Today I'd like to talk about revisit matrix completion, more specifically approximate low-rank matrix completion. Our main result actually is a new matrix completion algorithm which use a novel sampling scheme, which is a combination of several independent, which can be represented by a combination of several independent random bipartite regular graph. And based on the sampling scheme, so to simplify our result, we just assume that the rank, condition number, and the incoherence parameter of the matrix is are bounded as the dimension of the matrix n grows. So under this assumption, our algorithm would give O(n) sample complexity actually in linear time. So in 2010, a very famous result, Candice and Tao, they actually showed the information theoretical lower bound O mu 0 k and log n on the sample complexity for exact matrix completion under uniform sampling, where mu 0 is the incoherence parameter, k is the rank. And later on, many exact and approximate matrix completion algorithms actually proposed for this low rank matrix completion, achieving sample complexity O and log n and log n square. But here we ask another question. If we are only interested in epsilon approximation of the underlying matrix, for example, in terms of Frobenius norm, can we get rid of log n? For example, can we achieve sample complexity O(n), polynomial of log 1 over epsilon sample complexity? Here, our paper actually answers this question. We give a positive answer to this question. Here is a comparison of various approximate or exact matrix completion algorithms, where epsilon is the tolerance, such that the reconstructed matrix M tilde actually is the epsilon approximation of the underlying true matrix M in terms of Frobenius norm. Here we'll see before the results, most of the low-rank matrix completion algorithm they have a n log n sample complexity. But here, our result actually get rid of this log n. So in the last line, it's the sample complexity and the running time in our paper. So if we assume this like kappa mu 0 rank k is bounded, then our algorithm do give a linear sample complexity and a linear running time. Here, let me restate the famous low-rank matrix completion. The first is just the standard incoherence assumption, and the question is given underlying rank K matrix. Here we just assume it's a square, but without loss of generality, it can be very easy to extend to the rectangular matrix. The question is to design or select a sampling index set omega such that M can be reconstructed exactly or approximately from revealed entries. So here, I'll first introduce the sampling scheme we used. First, we'll introduce a graph representation of the sampling scheme. Imagine you have a bipartite graph. Each on the left-hand side, you have n vertices. Each vertex represents a row of the matrix, and on the right-hand side, you have another n vertex. Each vertex actually represents a column of the matrix. For example, if the ij entry of the underlying matrix M is sampled, then we create an edge which links the ith vertex on the left-hand side and the jth vertex on the right-hand side. Then for each sampled entries, we create a vertex in this bipartite graph. Then it's a equivalent representation of the sampling scheme. Now we introduce another concept, which is a random bipartite deregular graph, which is a graph which is chosen uniform at random from all bipartite deregular graph. D means each vertex has a degree D. Now our sampling scheme actually is there's a capital N here. Just assume it's just treated as a constant. Later on, reveal how large it is. So our sampling scheme actually is 2 capital N plus 1, a combination of independent random bipartite deregular graph. So we call it as a random deregular graph model. So let me introduce another component in our algorithm. So we call it a single value thresholding. So for matrix capital A, So we just check it's a singular value. If it's a singular value, actually it's below root A. We just lift it to root A. A actually is a constant between 0 and 1. If it's a singular value, actually it's above root 2 minus A. We just truncate it down to root 2 minus A. For the singular value, actually between this region, actually we keep it unchanged. So we just denote it as a T2. As a operator, single value thresholding operator. Now we are going to introduce our algorithm actually as the vanilla alternate minimization. It's very similar, but here I do need to. There's a very famous result, the Mars result, the local minimizer for matrix completion. Local minimizer, actually global minimizer. Actually, in this sampling regime, we have only ON samples. I do not think this result would hold in this sampling regime. So actually, I do some experiments. There actually is several local minimizer, which is not a global minimizer. So we do need this initialization. We call it, yeah. So this is our the TC iteration of our algorithm. So we first check. Actually, it's just a very famous alternating minimization. I think everyone are very familiar with this algorithm. So the only difference, of our algorithm from the vanilla alternating minimization is we first check actually net matrix. Just check its singular values. So actually, we can do some calculation of net matrix. The expectation of net matrix actually is identity matrix. So what we do is we just check its singular value when it deviates from its expectation. If it does not deviate from its expectation, we keep it the same. If it deviates from its expectation, then we do singular value thresholding. Here, the difference, because we do not have a under this sum, we have only constant number of entries, so we do not have a concentration inequality here. Previously, in the analysis of the ordinary minimization, people do use some like Bernstein inequality to say, oh, this matrix actually is well behaved, but here there's some yield conditioning here. We do use this singular value thresholding to get rid of this difficulty. But one essential analysis challenge here is we do need to control the regularization we enforce in this algorithm. So one key idea behind our algorithm actually is the regularization of a least square estimation in the form of singular value thresholding. Here is our main result. So when the degree d actually is at least the right-hand side on equation 1 after log 1 over epsilon iterations, our algorithm is guaranteed to produce epsilon approximation of the underlying true matrix. So here, this slide actually characterized the impact of the regularization. This set SBT beta actually characterized the number of times in each iteration the single value thresholding operations are applied. So actually, this result is the most technical result in our paper. So we do use very heavily use the detailed structure of sparse random regular graph to derive to control the impact of this regularization. So you can see from the right hand side, it's a very small portion of n. So based on this result, we are able to control the impact of the regularization. Our last contribution is the conjecture. Actually, so we conjecture that this algorithm also gives the same sample complexity even under uniform sampling. The intuition behind this conjecture is that for a graph, if you are familiar with the graph theory, for a large degree, actually the random regular graph behaves very similarly to the Adoshi-Renyi graph. So that's it. Thank you.
Any questions?
Sorry.
Okay, let's just thank all the speakers in this session again.